Hello and welcome to my new video, and I am going to do an example for the short circuit and an open circuit test, and you will see how that is done, and I'm going to explain some things. So I'm just gonna read the example. It says tests are performed on a single phase. If you don't see, this is one phase, 10 kilovolt ampere, 2200 divided by 220 volts, 60 hertz transformer, and the following results are obtained. For the open circuit test, no voltage, no load is the same as open circuit test, so that's the same thing. So you can say open circuit because one circuit is open, or no load because you don't have a load. The high voltage side is open, so in this you always measure the open circuit test from the low voltage side because it's a better reading, and we had these results. The voltmeter showed 220 volts, the wattmeter showed 100 watts, and the ammeter showed 2.5 amperes. And for the short circuit test, low voltage side shorted. So for a short circuit test, the low voltage side is shorted by an ammeter, and the following measurements were 150 volts showed the voltmeter, 4.5 ampere is the ammeter is showing, but on the high voltage side, and 215 watts on the high voltage side. Okay, so this example, because I need some room for this example space. The first, by A, we need to derive the parameters for the approximate equivalent circuit referred to the low voltage side and the high voltage side. So all those parameters that I showed in my last videos, the X's, the R's and everything, we need to determine them. By B, we need to express the excitation current as percentage of the rated current. That's easy. And by C, we need to determine the power factor for the no load and short circuit tests. Okay, so we need to derive the parameters, we need to calculate them from the low voltage and the high voltage side. We need to express the percentage of the excitation current of the rated current, and determine the power factor for the no load and the short circuit test. First of all, what are the transformer ratings? Those are the ratings which manufacturers guarantee that the transformer is going to work periodically. So what are the transformer ratings right now? Well, as you can see, it says here the tests are performed on a single phase 10 kilovolt ampere on transformer. So the transformer works on a 10 kilovolt ampere power, the apparent power. This is the apparent power. The primary side of the transformer works for 2200 volts. So it is designed that the primary side can have 2200 volts, so you have to bring some sort of high voltage winding for the primary side, and the secondary is 220 volts. So those are the ratings of the so for this and it is manufactured for the 60 hertz frequency. Now we know that it has 10 kilovolt ampere power. So what are the currents in there? So now the provided voltage, the rated voltage is from the high voltage side, VH rated is 2200 volts, and this in subscript H represents high, and low voltage side, rated low voltage side is 220 volts. So what is the current, rated current on the, what is the rated current on the high voltage side? Well, you know that the apparent power is equal to the voltage times the current, so the current is equal to the apparent power divided by the voltage, and then the high rated current is equal to 10 kilovolt ampere, so that is 10,000 divided by 2200 volts, and that is 4.55 amperes. And the rated current for the low voltage side is 10,000 divided by 220, and that is 45.5 ammeters. So these are the rated values on the of the transformer. So the transformer is going to work properly with these values. You don't want to give it a higher value of the voltage. You don't want to have higher values of the current, because it's going to burn the transformer. And just few more things. As you can see, the open circuit test, high voltage side is opened. So on the high voltage side, we bring 220 volts. As you can see, 220 volts. And why is the current less, 2.5 amperes? Because in an open circuit test, you only have an exciting current. So this here on an open circuit test, this is the exciting current of the transformer. And but you will see that later. And on the short circuit test, when you have a short circuit of the transformer, it draws a lot of current. So there is no load, and that is very there is a load, but it is its impedance is very, very small. So you have a short circuit, and that draws a lot of current. So we don't bring on the high voltage side 2200 volts, because then the current is going to be huge. So we manually raise the voltage from 0 to some value when the ammeter is going to show 4.5 when it's going to show the rated current of the transformer. So first of all, you need to know the rated values. These parameters here are on the nameplate on the transformer. You calculate the rated currents, and then for a short circuit test, you raise the voltage on the high voltage side, to the point where the ammeter is going to show the rated current. So it's 4.55, here is 4.5, but in real life, as an engineer, you need to know that. So for a short circuit test, you raise the voltage to that point when the ammeter is going to show the rated current. Okay, now we can determine the parameters. So I'm gonna remove this, and this you write this down to have it. So we need for B, when we want to determine the percentage of the exciting current from the rated current, we need to express the exciting current from the rated current, but that's for B. Now I just wanted to know what are transformer ratings, and how do we measure this? In which values do we go for these tests? Now I'm gonna remove this. So by A, we need to derive the parameters for the approximate equivalent circuit referred to the low voltage side and the high voltage side. So first we have an open circuit test. So high voltage side is opened. Now the low voltage side acts as a primary. So here we have VL. Now we don't have the resistance and the leak of the winding and the flux leakage of the transformer are neglected in this experiment. So we only have a shunt branch. We only have the shunt branch of the equivalent circuit. Now, and we have the current, exceeding current of 2.5 amperes. Now in subscript I put L and L and L, so this is the low voltage side. And the branch over here is now disconnected. Now, how we can determine the value RCL? Well, the wattmeter showed 100 watts of power, and that goes to the resistive, to the active loss, and the active loss goes on the core loss, which is equal RCL. So now you know that P is equal to voltage squared divided by R. So this is the open circuit wattmeter, this is the low voltage, and this is the core loss on the low voltage side. Now you can express the resistance of the core loss, that is equal to the low voltage squared divided by the power, and that is equal to 220 volts squared divided by 100 watts. Let me just see what is the value, and we get that RCL is equal to 484 ohms. Okay, now what is the current ICL on the core loss? Well, that is easy now, because by Ohm's law we know that the voltage from here to here is the low voltage VL, and then ICL is equal to the low voltage divided by the resistance. We get 220 volts divided by 484, and that is equal to 0.45 amps. Now we can calculate the magnetizing current, and with Pythagoras theorem. I showed that in my previous videos, and that is equal to the exceeding current squared minus the core loss current squared, and all that is on a square root, or power by 1/2. Then we have 2.5 squared minus 0.45 squared, all that on 1/2, and that is equal to 2.46 amperes. Okay, so this is the magnetizing current that magnetizes the magnetic circuit. Okay, now the reactance of the magnetizing current, magnetizing circuit, is equal to voltage, which is equal to VL. You know that this is on the same potential, so VL divided by the current. We get 220 volts divided by 2,46. That is equal to 89,4 ohms. Now, this was from the low voltage side. Now we want to transfer this value from the to the high voltage side, and because the high voltage side acts now as a secondary. Why do we say that? Because we brought the supplied voltage on the low side. So from the high voltage side, we do the impedance transfer like it was secondary. So the high voltage side, the core loss for the high voltage side, capital H, is A squared divided by RCL. Now, how do we know what is the turns ratio? Well, look at this. It says that the voltage is from the primary side of the turns of the rated voltage, V1 divided by V2, which is equal to A. You have 2,200 volts divided by 220 volts. So the turns ratio of this transformer is 10. Then you get the high voltage from the high voltage side. The core resistance is A squared. That is 100. 10 squared is 100 times. We have that for the low voltage side, RCL is 484 ohms. And then we get 484 and 48,400. So you just add 2 zeros on the end. And the reactance is the same. And this is equal to, this is for the high voltage side, A squared times, and that is equal to A squared is 100 times this, 8,940. Yes, ohms. Now, just a second, I'm gonna make this a little bit better. So this is the low voltage side. The core loss is, the impedance of the core loss is resistive, so we just put here 484 ohms, and the impedance of the magnetizing, the impedance of XM is equal to imaginary number, small letter J, and from the low voltage side 89,4 ohms. So this is the low voltage side, and high voltage side is equal to 10, and the high voltage side now looking this from the high voltage side, this here is equal to 48,400 ohms, because we made an impedance transfer from the high to the low voltage, and the impedance of this XM high is equal to J8940 ohms. Now this is the high voltage side, and we need to calculate what is the equivalent resistance in this branch here and in this branch here from the short circuit test to determine R equivalent H, X equivalent H, and for R equivalent of the low voltage side and X equivalent for the low voltage side. So these are the winding resistance looking from the high voltage side. This is the reactances of the flux leakages from the high voltage side. This is the resistance of the windings looking it from the low voltage side, and this is the reactance of flux leakages for looking it from the low voltage side. So this here goes here, and this here is gonna go here in series. Now I need to remove all this, and we're gonna calculate these parameters. So for the short circuit test, we don't have a shunt branch, so this shunt branch is removed in a short circuit test, but we have the resistance R equivalent times the X equivalent in the short circuit test. So now we measured it in a short circuit test. These here parameters are performed on the high voltage side. So now this is a primary, and this we're gonna first calculate the high voltage side parameters. Now how do we do that? Well, we know that the voltages here is 150 volts, but that doesn't make this isn't important now as the current, and we have 215 watts of power. Now this 215 watts power goes on the active values of the circuit, and the active on the active power loss. Now, and the active power loss goes on the resistive side of the transformer, and this is the reactive. Now we don't have a reactive wattmeter, we only have active wattmeter that shows the active power, and the active power goes on the resistance of the windings in this circuit. And yeah, the exceeding current is very low. You will see that it's 5% of the rating current. And yeah, let's calculate this now. So the active power goes on the active side, and the formula now, this current goes 4.5 amperes go like this. This is short-circuited, and the 4.5 amperes go to this resistor. So the power on this resistor is I squared times R. Now R equivalent H is equal to the power 215 watts divided by I squared, and the I squared is 4,5 squared. Now this is equal to 10.4 ohms, and then this R equivalent H now goes here. Okay, now I think you understand what is this is now looking from the high voltage side, the resistance of the windings. But for the low voltage side, because now the low voltage, this one now the low voltage side now here was on a secondary, and to make this as a and to transfer it on the low voltage side, our equivalent L is now equal to R equivalent H divided by A squared. And that is equal to 10,4 divided by 100, and you get 0.104 ohms. Now here you have the resistance of the windings, looking at it from the low voltage side, 0.104 ohms. I'm gonna remove now this, I don't need it. Okay, now we need to calculate the reactance equivalent of the high voltage side, and that is equal to the Pythagoras theorem, like this, Z equivalent high squared minus R equivalent high squared, and all that one half. We have a series resistance, but you know that for the intensity of the amplitude of this, you need to measure it from the Pythagoras theorem. But how do we know what is the equivalent impedance? Well, you know that the equivalent impedance of the high voltage side is equal to the voltage that you measured divided by the current, and that is equal to 150 divided by 4,5, and that is equal to 32,97 ohms. Now, from here to here, X equivalent H is equal to Z equivalent H squared, that is 32,97 squared, minus 10,4 ohms squared, and all that on 1/2. So it's a square root. This here, it's hard to draw the square root, so we just put that all of this is equal to on 1/2. And when you calculate this, you get 31,3 ohms. So here now we have the equivalent reactance 31,3 ohms. Now here, instead of the resistor, and here I made a mistake, I should have put an inductor. So you know this is a reactive impedance. And now the equivalent on the low voltage side, we have X equivalent H divided by A squared. So why do we do that? Because on this, looking at this, here is the high voltage side on this part, and to transfer the values from the high to the low, here we had this acting like a secondary, and moving from primary to the secondary, we need to divide by A squared, and that is equal to 31,3 divided by 100, that is equal to 0,313, and you put this J 0,313 ohms. And here you had, so this is the low voltage side and this is the high voltage side, and so we determined the equivalent parameters for the low voltage side and the high voltage side of the transformer. Now it asks express the excitation current as a percentage of the rated current. So I said on the no load open circuit test or no load test, this here is the exciting current, because we don't have the resistance is neglected. It only goes to magnetize the current. So this is it. The exciting current is 2.5 amperes, but from the low voltage side. And if you remember earlier that the rated value of the low voltage side was 45,5 amperes. Now the rated the percentage of this is very easy. You divide 2,5 with 45,5, multiply that by 100, and you get 5%. Now, as you can see, the exciting current of this transformer is only 5% of the rated current. Okay. Now, what do we have to calculate? Oh yeah, we have to calculate the power load. The power factors of the no load test and the short circuit test. So you know that the power factor is equal to the power divided by volt ampere. So this here, so when you divide the active power with the apparent power, the full power, you get the power factor of the circuit. That is the cos phi, if you remember it. And we don't put number 3 here because it's a one-phase circuit. It's not three-phase. So the power factor of the no load, power factor no load, or open circuit, sorry, you can write it open circuit, no load, that's the same thing, don't mix it up, is equal to the power, 100 watts, divided by the apparent power, the full volt ampere power, that is equal to 10,000. Oh, sorry. The apparent power is not this, because we used other measurements. The apparent power is equal to the voltage times the current in alternating currents, and that is 220 volts times 2.5 amperes. And the power factor at no load is 0.182. Now I don't know if this tells you something, but at the no load you can see most of the power is reactive. Looking at this, because you don't have much resisting materials. You only had magnetizing, more magnetizing material, so more reactive power to magnetize the magnetic circuits. And the power factor of the open circuit, short circuit, you will do for homework. See you in my next video.